Okay, good to go. We're going to continue with the lecture. We just finished giving you the homogeneous transform for the cyclopean eye. One thing I'd like to add at this point is the pair of transformations that will make it stereo, so that I can give you right and left eyes. So if you want to do that, we get T, let's say left eye, which is equal to, let me make an identity matrix first. Not a very good identity matrix. Let's see there. And then put TI here. All right, so I guess left eye is equal to TI if I do this transformation, because this is just the identity. So I just want to do a little fix. So basically, the horizontal direction from the coordinate system we set up is the x direction, correct? So I just want to take the x part here, this is the x translation part, and I want to put some shift in there. I will call it t over 2, where t well, let's see here. Is going to be the inter-eye distance in the virtual world. So t is the inter-eye distance in the world. And if you're curious about the real world, the t average value in the world, I mean in the real world in this case, right, like on the earth, among humans, not among the monkeys running around on your campus, but among the humans, is equal to 0.064 meters, or 64 millimeters. So that's just an average. There's quite a bit of variation from person to person, and this is a nice example of when you define the world, it's good to use whatever system of units you use in your daily life. So if you're using the metric system here, it's nice to set that all up so that your units in the world are meters, so that then when you perform this shift here, this makes appropriate sense, because we're still using the coordinates of the world here for the eye. We haven't done any strange distortions or rescalings yet, right? These are all rigid body transformations, so it's okay to use meter coordinates. And for the left eye, I do this transformation. So is that, does this need to be, I guess one question I need to ask here, does this need to be minus or plus? What do you think? So let me think about this. So I start off with a cyclopean view, and then I want to figure out what the perspective should be for my left eye. So if I all of a sudden move my eye to the left, that means I should be shifting the world to the right, which means that I'm adding to the x coordinates. So that's what I get that. Very easy to mess this up. In fact, in one of the very first Oculus demos we were working on, the right and left eyes were swapped, and everybody in the company thought it was fine for a while. It was very difficult. You had to eventually look around the edge of some corner so that your left eye can't see beyond the corner and your right eye can, and you realize, hey, something's not right here, and you have to learn to open one eye and close the other and try to resolve these things. That gets into the perception parts again. So your brain cannot necessarily distinguish when you make some of these mistakes. So that's T left eye, and for T right eye, it's just the other way. We just use the other sign. We just put minus T over 2 here, and then fill in the, oops, sorry, it's 1. We fill in the rest of the identity matrix. And put TI here. So in that chain of transformations I gave you, if you want to go from cyclopean eye to binocular vision, having left and right eyes, then you just replace TI with T right eye and T left eye, and that will give you 2 different paths to go down for the rest of the chain to fix everything. You can try to do some hacks at the end where you just shift it all the way down in the pixel coordinates, but you may make mistakes. So it might look okay in some cases, it may cause errors in others that are perceptible. So this is the right way to fix it, even though it might not be the most efficient way to fix it, it's correct. And so there are other ways that may be more efficient, but they're hacks and they may make mistakes. We can talk about some of those kinds of things later in the course. Questions about this? Yes? The angle. Oh, I see. So, well, this is going to be okay. This is still changing just the viewing. I'm still. I see what you mean. So you want to, if they're both fixated on a single point in space, right? Then you're right. There will be some vergence, and that's something separate that we're going to cover. We're not going to present images to the eyes based exactly on which way they are oriented with respect to your head, because we're not doing eye tracking. If we additionally add eye tracking, then we would have to also consider the individual rotations of the eyes as they converge. And our brains are considering that certainly in the real world, and they're taking that part into account. But if we're just going to render onto a display, it will be an assumption that the center views of the eyes are in fact the same. So the eyes are in fact looking off at infinity, at something infinitely far away, and we're not taking the vergence into account. Well, that's a very good question, though. Yeah, it's interesting. So we're neglecting that part, and it's okay here. But in some other system where you're taking eye tracking into account and you're presenting to the eyes exactly what the eyes are looking at, considering their rotation, this is called foveated rendering, for example. It's more expensive to do that now and less clear how to solve all the engineering challenges, but it can be done. And if that is done, then you would have to take that extra transformation into account. Other questions?